Welcome to this lecture. In this lecture we will transition from neural networks and also the parametric class of algorithms that we were looking at so far to class of non-parametric algorithms. We have already seen examples for non-parametric algorithms, right? The nearest neighbor is one non-parametric algorithm where you do not start by assuming a functional form for the hypothesis and estimate the parameters. However, in a non-parametric way, without assuming a parameter for the hypothesis function, you solve the problem of classification or regression is the idea behind non-parametric models. So far in neural networks, for instance, the idea is to express the hypothesis function using a parametric set which we denoted as h theta and estimate the theta by minimizing the KL divergence or empirical risk minimization. In non-parametric models, we do not explicitly define the model using parameters, but we implicitly learn the decision boundary itself, okay, through ERM. So, that is the idea. So, one famous example or often used example for a non-parametric model is what is called as classification and regression trees, or also known as decision trees. So, we will look at decision trees, the naive decision trees for classification and regression, and then we will discuss about the problems associated with the decision trees. It often tends to be a classifier that has very high variance. So, we will look at ways to reduce the variance of these decision trees. A classifier or a hypothesis function that has very high variance is equivalent to overfitting the data. So, decision trees, the naive decision trees tends to overfit the data. So, then we have to look at the ways to either increase the bias or reduce the variance. One of the ways to reduce the variance of any classifier in general is by using this algorithm or technique called bagging, okay, where also known as ensembles, where you, instead of training one hypothesis, you train multiple hypotheses on the same data via a sampling procedure and aggregate them, and we will see mathematically why this sort of an aggregation leads to reduction in variance. Okay. So, combining decision trees with bagging will give us multiple algorithms that are used in practice. One of the very famous algorithms is what is known as random forest. Okay, we will look at what random forest is, and there is another set of algorithm which is again bagging, but instead of we do sampling in a slightly different way. These kinds of algorithms are called boosting algorithms. We will look at two specific boosting algorithms. One is the XG boost or gradient boosting algorithm, the gradient boosted trees, so to speak. The other class of algorithms that we will look at is what is called as AdaBoost. Okay. And I will show that all of these are empirical risk minimization with a particular loss function and a sort of regularizer. So, that story still remains. So, that is how we will move on right now. Okay. So, now let us start with the naive decision trees. Now, so let us consider what happens when we build a classifier before we go on. So, when we build a classifier, so what actually happens is that the space in which the data lies. So, let us say that X or data is in R2 for ease of understanding. When you build a hypothesis function, okay, what happens is that the space in which the data lies gets split into regions. For instance, if we are looking at linear discriminant functions, okay, then what does the classifier do finally? It splits the ambient space or the data space into two non-overlapping regions, isn't it? So, if the data falls in one particular region, then it is designed as, I mean, it is defined as one class, and if it falls in some other the other half or the other part of the data space, it is defined as another class, isn't it? Now, even if it is a let us say, see, there is no reason why your hypothesis should split the space into contiguous regions. So, it can be even discontiguous regions as well. Specifically, if you have a k class classification problem, it actually happens that way. So, remember in your assignment I talked about one versus rest approach, right, where You solve a k-class classification problem by solving multiple binary classification problems, right, where every binary classifier would answer this question whether this sample belongs to the kth class or not. Combine multiple of these classifiers, you get a k-class classification problem. Even otherwise, when you solve a multi-class classification problem, let us say using a neural network, what is actually happening is if you have k classes, the data ambient space gets partitioned into k different regions. During inference, a data point falls into one of these k regions. Depending upon where this data point is falling, we define, we assign that particular data point during inference, that particular class. Do you see this happening? So, every classification algorithm, okay, geometrically is partitioning the data space into multiple regions. Do you see this? So, this is actually the foundational idea behind decision trees. So, now what we do is we explicitly partition the data space into several regions, okay, and this is what a tree does. Think about it. What is a tree? I mean, I am assuming that all of you know this idea of growing a tree, okay. So, what happens is, suppose I start asking questions like, let us say that I have data which is in one dimension, or rather one dimension for understanding sake. So, what I will do is I will start asking questions like whether a given data point is above this threshold or below the threshold. If it is above some threshold, I will go to one branch in the tree given a node, or if it is below the threshold, I go to the other branch. And at the second node, I ask the same question whether this thing is greater than or less than another threshold or so on. So, what am I doing at every node? Okay, I am drawing a line which is parallel to the axis, because every threshold that I put on a scalar feature is equivalent to drawing a line that is parallel to the axis, is not it? So, x equal to tau is a line that is parallel to the coordinate axis. So, at every level or every node, I ask a question whether this particular data point takes a value that is greater than a threshold or less than a threshold. And if I do it hierarchically in a tree based fashion, what am I doing is explicitly dividing the data space into multiple regions. Do you see this? You understand what I am saying? Now, suppose we have data of, let us say, d dimensions. When I grow the tree at every node, okay, I take one dimension of the data and ask a question on its threshold, whether this particular feature is greater than this threshold or less than this threshold. So, now if I have several nodes, okay, so every node in a tree, in the naive decision tree, asks a question on one dimension of data. Does it make sense? So, I have a tree, okay, may not be binary, okay, and this tree has several nodes, and at every node the question that I am asking is, I take one dimension of data and I compare that dimension of data with a threshold, as a fixed threshold. If that is greater than threshold, I move to the left. If it is less than the threshold, I move to the right.
This is done for every dimension?
This is done for every dimension of data at every level in the naive formulation. Okay. This is how I construct a tree. So, now there are questions, there are lots of questions to be asked. Now, how do you choose what threshold to be taken? So, that is what we learn. See, when we train a tree, what we learn is what threshold has to be chosen, okay, at a particular node, and how many nodes have to be there, how deep the tree should be, and so on. Once, suppose you have this sort of a tree constructed, during inference what do? Given a data point, okay, you traverse this tree entirely, and leaf nodes should correspond to classes. But what typically happens is, I mean, let us say for assumption, I mean for discussion sake, even leaf nodes correspond to a region. See, what I actually want you to understand and appreciate before we go to the math is that when you construct a tree, every node is splitting the data space into a region. So, every node corresponds to a region is what is to be understood, okay, and what region a particular node corresponds to depends upon what questions it asks at that particular node and also its predecessors, because after having asked multiple questions you come to that particular node. So, therefore, every node has to be seen as a partition of data. Is this clear? This is actually the most important thing in growing the tree. Everything else is mathematical detail. So, every node in a tree corresponds to a partition of data space into regions. Now, finally, how do you decide the class is that at the leaf node, okay, when a data point if a data point has traversed the tree and ended up at a particular leaf node, it actually means that this data point belongs to a region that is defined by the leaf node, that particular leaf node. Decide the class of that data point by looking at the majority voting of all the data points that are training points that are already there in that particular region. That is how you do it. Do you see that? Right? In fact, it is like softmax. At the leaf node where a data point ends up, okay, let us say that there are 3 points from class A or class 1 and 7 points from class B, then this particular test point will be classified as class 2 with 70% probability, class 1 with 30% probability, just like softmax. Okay. Now, the question, this is what you do during inference. Now, the question is, how do you construct the tree given a training data? What are the parameters that we have in constructing the tree? The thresholds. So, how do we choose the threshold such that this makes sense? So, that is what we will look at.
The number of nodes.
Number of nodes is typically a hyperparameter, it is not the parameter. So, the parameters are these thresholds. Is this all right? Any questions so far? Because one particularly important point that I want you to understand is that every node in a tree is a region in the data space.
And the number of leaf nodes will be the number of regions or classes.
Not necessarily, because as I said, right, once the data point traverses through the entire tree, when it comes to the leaf node, see what proportion of the training points in that particular region belong to a particular class, and then assign this test point that class that corresponds to the majority vote within that region. That is it. Yeah, is this idea clear of how a decision tree works? Any questions on this? Now, let us look at the math. Decision trees. So, these are nonparametric methods. The core idea is to split the data space into regions via binary questions, mostly binary questions on feature dimensions or data dimensions, let us say. Right. Now, okay. So, mathematically, suppose so we have the data set D, which are points that are still have their ID drawn from Pxy. We have x in Rd, and for now let us say that we are looking at classification problems. We will discuss about the regression problems in a while. So, we have classification problems. So, at any node, at any given node M, which represents a region Rm. What is a region? Region is a subset of the ambient space, right. every region is a subset of the entire data space Rm. So, containing nm samples. So, every region contains a certain number of training samples, right. Let us denote that by mn. So, a node is a region and that has a certain number of training samples within it. The moment you define a subset in RD, it will have some samples from the data set D, right. Nm samples from D, that is explicit. The tree algorithm asks a binary question. As follows. Suppose xj denote the jth dimension of x, okay, and t be a scalar threshold. The question is, if xj is less than or equal to t, go left. I mean, not question, we will see this as an algorithm, a split. Xj is greater than t, go right. That is it, okay. So, at every node, the question that I am asking is the split is defined this way, that if jth dimension of data is greater than a particular threshold, take one branch, if it is less than it, take the other branch, okay. So, please note that this is a discrete space. We cannot use gradient descent kind of algorithms that has derivatives to get this split, okay. So, we will have to adopt a greedy algorithm. The exhaustive way to do it is to take at every node, consider all data dimensions and all particular thresholds, okay, and choose the one that optimizes whatever the objective that we look at right now. But that is not possible, right, that exponentially prohibitive, that is an NP complete problem which cannot be solved. That is why decision trees are greedy algorithms, and there is no optimality which is guaranteed because of this particular reason. They are greedy optimizations. So, what do you mean by greedy? You take a decision and never go back without thinking about optimality, right. At every step you take a decision greedily, okay. So, do you all see that it is actually an NP complete problem that is exponentially large, because even if you assume threshold to be discrete, okay, then you will have to evaluate all possible thresholds at all nodes at all depths of the tree for all features, which is not possible. So, you will have to do you will have to take the decision in a greedy way, okay. Now, at every node the optimization objective for split so at every node search over every feature, every data dimension and threshold which is represented as a pair j comma t, right? J is the index of the data dimension and t is the threshold, that maximizes or that minimizes the node impurity. That's the idea. So, what are the choices that we have? We will have to choose a pair of data dimension and the threshold, choose that pair of data dimension and the threshold that would minimize the impurity of a node or impurity of a split. So, what do you mean by impurity of a split? It is pretty simple. Let us try to understand this. So, when do you call a split meaningful is the question. Okay. Now, remember that every node or every split is partitioning the data. So, what data partition is called a good partition? A good data partition is the one that has all samples corresponding to one particular class, is not it? Why? Why is that a good partition? Because remember that finally what do we have to do? Any classifier would have to partition the data space in such a way that one space always contains samples from one particular class, the other space contains samples from the other class. That is what separability is all about, right. So, when you define a subset of region, subset of data as a region and you define goodness or purity of that region, a good metric is the one, or rather a good split is one, a good region is one which contains samples from only one class, right. Probabilistically, what does this mean? This means that the distribution of one particular class has to be Dirac delta. It should be as far from a uniform distribution as possible. If the distribution of classes uh, within a particular region is uniform, then it is a impure region. Why? Because if you end up being in that particular region which has a uniform distribution over all classes, then it is not a good region because you are not giving any more information, is not it?
All the classes are present in the same region.
All the classes are equally represented in that region. So, you do not want to end up in such a region. So, a good region is one where the distribution over classes of those samples within that region is as far away from uniform distribution as possible. Okay. Now, how do you define farness or closeness from a distribution? Scale divergence, right. So, you have to compute the scale divergence between the distribution of classes within a region and the uniform distribution over those discrete samples. And fun fact is the scale divergence between a given distribution and the uniform distribution is entropy, right. Because just do this, I mean I take it as an exercise, show that if you take a distribution and compute its scale divergence between a uniform distribution over the same sample space, you will end up getting entropy. So, in other words, what are we saying is minimize the entropy of a particular region, entropy of the distribution of data within a particular region. Okay. So, let us look at, so basically you have to minimize the impurity. Let some I of r be the impurity function So, the cost associated with a particular split or a node j comma t is impurity associated with the region of the left node plus impurity associated with the region of the right node, where NL and NR are number of samples that traverse the left and right regions RL and RR respectively. So, L, which is the metric that we are trying to minimize, is the weighted impurity, right, associated with the regions that we get after a split. So, when we split, we get two regions, right, RL and RR. Okay. Now, compute the impurity associated with RL, compute the impurity associated with RR, okay, weight it with the number of samples that both of the nodes get with respect to the total number of samples that are there in the particular node, and minimize that metric. That is it. Does it make sense? So, this is the abstract algorithm of how a decision tree is grown. Okay. Now, we still have to decide what I to be chosen. So, one I already told you, right, the entropy is one. There are other metrics also. We will look at two of them, one the entropy, the other is what is called as Gini impurity. We will look at both of those metrics, but the basic idea is the following, right. When you split, you will have to split in such a way that the impurity function associated with the weighted impurity function associated with that particular split has to be minimized. Make sense? Okay. Any questions here?
What is this L?
Yeah, this is the function that we are trying to optimize for. So, when we split, we will see what we do algorithmically is that at a given depth and a node, when we have to define a node, we will compute this for all possible j and t, okay, and choose one that would minimize this. Okay. So, what do you mean by choosing one? What we actually choose is a j and a t, right. Every node is a pair of j and t, that is what I want you to understand. You choose a data dimension and you choose a threshold, and the questions are always this, if xj is greater than t or less than t, that is it. Now, how do you choose a particular dimension and a pair of dimension and the threshold is by minimizing this loss, okay, which is the weighted impurity function split across two particular regions. Is this all right? Okay. Right. So, now let us look at choices for the impurity function. See, as a side note, most of the recommendation algorithms and the classification algorithms that are used in industry at very large scale are based out of random forest and decision trees. Okay. In fact, so much so that when we were students, there used to be these global competitions on some data sets, and people used to explicitly ban the usage of random forests and decision trees as an entry for the competition, because one, bagging can be shown theoretically to increase, or sorry, boosting can be shown theoretically to increase the accuracy of a classifier. Ensembles are known to increase the accuracy of a classifier. So, ensembles were banned, and when ensembles are combination of multiple classifiers, individual classifiers for decision trees because of the ease of their implementation. Okay. So, that powerful. Okay. So, let us look at example impurity functions. The first thing that is often used in trees that are called ID3, C4.5 and so on, these are names of algorithms, are entropy and information gain. Now, suppose Pk is the proportion of training samples from class K in region Rm. What is Pk? The number of samples from class K divided by the total number of samples in in region Rm. By the way, what is this pk? If you recall the earlier classes, this is the ML estimate of that probability. The maximum likelihood estimate, okay, for a discrete random variable is the proportion of the number of samples from class k, isn't it? Right. So, if pk is the is that ML estimate, so we define the entropy of a node h of Rm simply as the, how many classes were there? K, capital K number of classes, so pk log pk. This is log to base 2, of course, right. This is the usual definition of entropy. This is how we define the entropy of a particular node. What is this? This is the KL divergence between this and the uniform distribution. Okay. Now, if it is 0, then that node is perfectly pure. If it is maximum, then that node is perfectly impure, right, and everything in between. Okay. So, now when a node is split, what do you want the impurity to happen? So, what do you want the impurity to behave like? The impurity has to decrease. When you traverse through the tree, okay, or when you split a particular node, the impurity has to decrease, right. So, now how do we measure that? The metric I corresponding to a particular split, okay, the impurity metric is the entropy associated with the parent minus the sum of weighted entropy So, this is one impurity metric that is used in practice. This one, right, this is RR, yeah. We have defined what RR is, it is the region that we get after we split to the right. Okay. Now, choose a split that maximizes this. It is the reason I said maximizing is that we need to put a minus here, right. So, or minimize the minus of it, we can say, does not matter. So, this is minimize the negative of this, because see this I, what is this? This is the difference between the entropy associated with the parent and the weighted entropy of the children. We want this to be maximized, because once we split this difference has to be maximized. So, negative of that difference has to be minimized, that is it. Okay. This is one measure that is used to construct the or split the nodes. There is another metric, okay, that is called Gini impurity. This is used because the entropy has a logarithm term in it, right. So, computing it is a little computationally expensive. So, if we can get rid of the logarithm term somehow and still get the similar effect, okay, it is better. So, that is why people sort of moved out of entropy and looked at a different metric. So, let us look at what Gini impurity is. Impurity should decrease. Negative of this is impurity, no. If you look at this metric, difference between the entropy of the parent and the entropy of the children, okay, is the inverse of impurity. This is purity. This has to increase, right. So, okay, let me not use I then, right. So, there maybe we can use this as, still use this as I cap. because sort of inverse of impurity, correct. So, this measures Gini impurity measures the probability of incorrectly classifying a randomly chosen point if it were randomly labeled. See, suppose you sample, there is a region, okay. You take you sample a particular point from that region, okay, and incorrectly label it, that is impurity, right. So, the odds of incorrectly labeling a particular point in a region has to be minimized, is not it, and when would that be minimized? If the region is pure. Suppose you have in a region all points corresponding to one particular class, then when you sample it and label it as I mean sampling it and labeling it as incorrectly is lesser, because all the points belong to one particular class in a node. So, this measure is looking at the odds of incorrectly labeling a particular point that is sampled from a particular region. Okay. How do we get this probability in terms of pk that we have written? What is the probability of choosing a particular choosing a point belonging to a particular class? So, probability of choosing a data point from class P or class K is pk, and the probability of incorrectly labeling it is 1 minus pk, right. So, the probability of incorrectly labeling is 1 minus pk. These are independent events, right. So, the Gini impurity associated with a particular region is, you have to sum this up across all possible classes, that is it. We want to split in such a way that this is minimized. So, we want to minimize the Gini impurity, right. I mean the probability of incorrectly classifying a particular point through random sampling has to be minimized, and this will happen if the node is pure. See, can you see this? I mean, it can already be seen, right. If pk is Dirac delta, this will be maximized. If there is a point, okay, if all the points within a region belongs to a particular class, then this will be smaller. The more the skewed the distribution is towards one particular class, the smaller this will be, right. That is algebraically it can be seen. Can all of you see that? The degenerative cases, when this pk becomes Dirac delta, that is when it is the most purest, the split is the purest. Okay. So, now what should we do? We should choose the split j comma t that minimizes the Gini impurity. Now, if you use standard libraries such as scikit-learn, they use Gini impurity, because computationally it is much simpler. In fact, what can be shown mathematically is that if you take the greedy way, okay, both entropy and Gini impurity based splitting methods will lead to the exact same split, is what can be shown. but because of computational ease, most of the algorithms implement Gini impurity over the entropy base split. Okay. Any questions here? Okay. So far we looked at decision trees for classification. What do we do for regression? We will stop here and continue in the next lecture.